Hello, student. Welcome back to this chapter of optical fibers. And in this session, I am going to derive an expression for this numerical aperture, and also we will have the condition for ray propagation. This is a very important part of this optical fiber as far as your examination is concerned. So most of the time, this derivation is asked. So in this diagram, you are looking at an optical fiber. Optical fiber is here, it is placed, and this red line indicates the incident ray of light going into the optical fiber. Here N0 is there. This N0 is the refractive index of air, and this N1 is there. This is the refractive index of core, and N2 is there. This is the refractive index of cladding. So this incident ray at the point O makes an angle theta naught here. So this, if you are rotating this ray vector AO about this axis, about the axis of this optical fiber, you will get a cone here, and all the rays which are inside this cone are accepted by the optical fiber. I mean to say that all the rays which are inside this acceptance cone will propagate inside the fiber fruitfully. That means they will undergo total internal reflection and propagate a long distance at a minimum loss. Because of that reason, this cone formed by rotating this light vector AO about the axis of the optical fiber is called as the acceptance cone. A cone is formed here, and this cone is called as the acceptance cone. So this is the incident ray. So at point O, the ray enters the optical fiber with an angle theta naught here. This is theta naught, and when it enters the optical fiber, it undergoes a refraction. So this theta is the angle of refraction inside the optical fiber. So this ray hits this point B. This point B is the point where it is at the interface of core and cladding. So such a point it is. So at the point B, the ray is grazing the surface of the core. That means this angle of incidence becomes the critical angle for this core and cladding. So because of that reason, when the ray hit the point B, and when it passes across the point B, it grazes the surface of the core, or it moves along the interface of the core and cladding. So this is what happens during the ray propagation inside an optical fiber. Same thing is written here. So in the diagram, a ray of light AO enters the core with an angle theta naught, and it refracts in the core medium at an angle of theta. So this is the ray AO enters the cone with an angle theta naught, and it enters the optical fiber, and after refraction at point O, it refracts through an angle theta. At point B on the cladding, the angle 90 minus theta becomes a critical angle, and hence ray grazes the cladding surface along BC. So this also I have shown here. For this point B, this angle is 90 minus theta, and that this 90 minus theta angle becomes equal to the critical angle for this pair of core and cladding. And because of that reason, after refraction, the ray grazes the surface of interface of core and cladding along the path BC. A cone can be drawn at point O by rotating the ray AO. So this is the cone formed by rotating this vector AO about the cable axis. And for any ray, for any angle of incidence which is within the cone, the ray either grazes the core cladding interface or gets total internally reflected back to the core. So this will happen. The ray propagates within the core with minimum loss only when the angle of incidence is equal to or less than the cone angle. This cone angle is called as the waveguide acceptance angle. So this also, so this is the cone angle theta naught, and all the rays which are inside this cone will propagate through the optical fiber with the minimum loss. And because of that reason, this cone is called as the acceptance cone, and this angle is called as the acceptance angle. And the sign of the angle of acceptance, sine theta naught, is called as the numerical aperture of the fiber. So this is another important parameter as far as optical fibers are concerned. And the sign of the angle of acceptance, which is sine theta naught, is called as the numerical aperture of the fiber. Here I will start the derivation, and let N0, N1 and N2 be the refractive indices of a surrounding medium, which is here and core of the fiber and cladding respectively. Now for refraction at the point of entry, that is which is the point O of the ray AO into the core, that means at the point of incidence, which is the point O, we have by Snell's law N naught sine theta naught is equal to N1 sine theta. And here N naught is the refractive index of air, whereas N1 is the refractive index of core. Theta naught is the acceptance angle, and theta is the angle of refraction inside the core. This is the equation 1. At the point B on the interface, the angle of incidence is 90 minus theta, and the angle of refraction is R, which is equal to 90 degree in this particular case. By applying Snell's law at the point B, we have N1 sine 90 minus theta is equal to N2 sine 90. Because here the angle of refraction R is 90 degree, So we have substituted R value here, and this is the angle of incidence. So this will simplify this equation. So N1 multiplied by sine of 90 minus theta is cos theta by trigonometry. So it is written as a cos theta and is equal to N2 into 1, because value of sine 90 degree, sine of 90 degree is 1. So it becomes simply N2, or cos theta is equal to N2 by N1. So let this be the equation 2. From equation 1, equation 1 was n naught sine theta naught is equal to n1 sine theta. From that equation, n naught I have taken into RHS. So LHS is left with only sine theta naught. So sine theta naught is equal to n1 by n naught into sine theta. This is equal to n1 by n naught into sine theta can be written as square root of 1 minus cos square theta by making use of the trigonometric formulas. So sine theta becomes 1 minus cos square theta under root. So this is equal to n1 by n naught into 1 minus n2 by n1 square. That means I have substituted the value of cos theta from equation 2. From equation 2, cos theta is equal to n2 by n1. So that is substituted here, and this root is there. And simplify this part of the equation, you will get this as square root of n1 square n1 square minus n2 square divided by n naught. Next, if the medium surrounding the fiber is air, most of the time it will be air, then n naught is equal to 1. Therefore sine theta naught is equal to root of n1 square minus n2 square. So here this n naught goes 1. So therefore we are getting sine theta naught is equal to square root of n1 square minus n2 square. So this sine theta naught is nothing but the numerical aperture by definition. So therefore the numerical aperture is equal to root of n1 square minus n2 square. Next, if theta I is the angle of incidence of an incident ray, then the ray will be able to propagate if theta I is less than theta naught. Theta naught is the maximum value of the angle of incidence required. So that means that is the acceptance angle. So for the propagation of the incident ray, the theta I, the angle of incidence, the theta I should be less than theta naught. Take sine on both sides, it becomes sine theta I is less than sine theta naught, and sine theta I is less than sine theta naught. Sine theta naught is nothing but the numerical aperture. So it is given by root of n1 square minus n2 square. So this is the condition for propagation. So that is sine theta I should be less than the numerical aperture. That means for the fruitful propagation of the ray inside an optical fiber, the sine of the angle of incidence, sine theta I, the sine of the angle of incidence, which is sine theta I, should be always less than the numerical aperture. And here I am going to define another important parameter called as the fractional refractive index change, which is denoted by the symbol delta. So this fractional refractive index change delta is the ratio of the difference of refractive index of core and cladding to the refractive index of the core of an optical fiber. So therefore, this delta is equal to N1 minus N2. This is the difference of the refractive index of core and cladding. So it is, so this two, we have to divide this quantity by N1, which is the refractive index of the core. So it's the equation 3. So this delta is always positive because N1 is always greater than N2 for the total internal reflection condition to be taken place. In order to guide the light rays effectively through a fiber, this delta, the fractional refractive index change delta, should be very, very smaller than 1. Typically, this delta is of the order of 0.01. Fibers with large delta will not be useful for optical communication due to the occurrence of multipath dispersion. And here a small relation between the numerical aperture and the fractional refractive index change delta can be obtained. So from equation 3, it is N1 minus N2 by N1 is equal to delta. So that equation you can write as N1 minus N2 is equal to N1 into delta. And numerical aperture is given by root of N1 square minus N2 square. This already we have derived. So this N1 square minus N2 square quantity can be written as N1 plus N2 into the bracket N1 minus N2. And this is equal to, you write N1 plus N2 as it is, and this N1 minus N2 from equation 4, N1 minus N2 can be written as N1 into delta. But N1 is nearly is equal to N2. That means the refractive index of core and cladding are not much differentiated with each other. They are having the nearly same value. So because of that reason, we can set N1 is nearly is equal to N2, and this quantity N1 plus N2 becomes equal to 2N1 here in this equation. So therefore, the numerical aperture is equal to root of this is 2N1 into N1 into delta. So it becomes 2N1 square into delta. So therefore, numerical aperture is equal to N1 into root of 2 delta. So this N1 square is there. You can take this quantity out of this square root. So it becomes N1. So remaining thing in the square root is square root of 2 delta. So this is the a simple equation or relation between the numerical aperture and the fractional refractive index change delta. So in the next class, I am going to discuss on the modes of propagation, which is called as the V number. Thanks for listening.